Okay, pre-calc, welcome back. Today we're continuing on with some angle stuff. And the first thing we're going to talk about is going to be pretty simple. If you remember, before one of the things we were talking about was finding, okay, so say I gave you the radius of a circle. Okay, so that's just a radius. And I gave you the length of the arc. Okay, so radius of the circle, length of the arc. And I can draw the other leg of it here. Right, so here we've got r, and our length of our arc we were just representing with an s. So given these two measures right here, can I calculate what this theta is, what this angle is? And sure enough, we were able to figure it out. We were able to derive that sure enough, theta, the angle, is just going to be equal to s divided by r. Okay, so we were looking for the angle given a radius and an arc length, or a circular arc. Here we're going to be talking about the length of a circular arc. And so we're looking for the arc, but we're given the angle. Okay, so here our objective this is going to be our first objective for this lecture, is we're going to be finding the length of a circular arc. Now, if you're comfortable using this equation right there, then you should be able to sort of really quickly rearrange this equation and figure out what you're looking for. Okay, so in this case, we're trying to solve for s. So if I have this function right here, theta is going to be equal to s divided by r. And if I take both sides, I multiply them by r, right? So then here I've got r divided by r. That goes away. It just becomes 1. So then I can just say, okay, s is going to be equal to r times theta. Wow, that's even an easier function to remember to use than this one over here. I don't even have to hit the divisible or the divided sign in my calculator. Okay, so let's go ahead and just jump right into an example. So example. So suppose a circle has radius of 10 inches. And so I want you to find the length of the arc intercepted by an angle of 120 degrees. Now that's going to sound a little bit crazy. Okay, length of an arc intercepted, blah, blah, blah. Okay, so basically what I'm asking for is pretty much what I've got drawn here. So I know I've got a 120 degree angle, okay, which is going to be roughly like this. Okay, I've got my r is going to be equal to 10 inches. So what is this length right here? That's what I'm looking for. I know that theta is going to be equal to 120 degrees. Okay, so what is this s? S is going to be equal to question mark. So sure enough, in this case, this is going to be a little bit tricky because this function right here, and I didn't mention this before purposely so that I could get to it here, but this function right here, it relies on the units of the angle, so angle units must be in radians. If you remember what a radian is, right? A radian is a relationship between the radius of a circle and the circumference of a circle, right? So if you took the radius and you brought it out and you bent it over the arc length, right, and you measured what that angle was, that would be a radian. And so that's exactly what we're talking about here. So we're talking about some chunk of the circumference, not the whole circumference, some chunk of it, an arc length like s. We're talking about the radius right here. So that's what this is. So angle units have to be in radians for theta. Okay, so here my theta is equal to 120 degrees. So before I do anything, I need to convert it. Now, hopefully you guys are screaming at your computers right now and saying, Dr. Craig, I know exactly how to convert it. I just take the angle measure in degrees and I multiply it by pi radians, pi rad, over 180 degrees. I'm going to say, Dr. Craig, we derived this in class. It's super simple, blah, 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 blah. And I'm going to say, fantastic, class. Nice job. And so sure enough, if we simplify this, or if we keep going, the degrees cancel out, and I just end up with 120 pi over 180. Or simplify it even more, I just get 2 pi divided by 3 rad. Okay, so that's my angle measure in radians. So now that I've got my angle measure in radians, now this problem is super simple. So I say, okay, my arc length S is going to be equal to R, which is going to be 10 inches, times theta. In this case, it's going to be 2 pi divided by 3 rad. And so this thing, and now radians, it is a unit, but effectively, if you check out your units here, we've got 10 inches multiplied by radians. The rad is it's a unit, but it's kind of a unitless unit. And this is hard to explain. Basically, it goes away anytime you multiply it by another unit, like kilometers or feet or whatever else you're using, time. And so if I do this, right, and so then I'll just end up with 20 pi divided by 3 inches. Okay, so that's going to be my units. And if you wanted to punch this into your calculator, pi and the 3, they roughly cancel out. But basically, you just end up, oops, you end up with, this is going to be about 20.94 inches. And so if I had a radius, right, a radius of 10 and degree of 120, sure enough, my arc length is going to be 20.94. So big takeaways here, okay? So equation, easy to remember. I've got my theta there. Big takeaway, though, is you got to remember that your angle units must be in radians. If you do it in degrees, imagine if I took 10 and multiplied it by 120 degrees. Right, I'd end up with 1,200 inches. Well, I know that that's not going to be right. Right, so I've got to make sure I'm in radians, 20.94. Now, done with that section. Now we're going to move on to a different problem. Now this is going to be another applied problem that I want you guys to think about. Okay, so our objective here, bringing all of this radian and degree and angle measure stuff back into the real world. So here we're talking about linear and angular speed. Okay, so our objective is to use linear and angular speed to describe the motion on a circular path. Okay, and this is actually really cool. There's tons and tons of applications of this. So I'm just going to jump right into it, and then we're going to get into some of the cool problems. Okay. So first we need to define what linear and angular speed is, right? So linear speed, think back to physics. So I've got some guy in a car, right? Or say I've got some guy running, right? I'm reading the Maze Runner right now. So imagine I've got some guy running here. Running along, okay, and I'm looking for what is his velocity. Well, assuming that his velocity is constant, right, all I need to do is basically when he crosses me here, right, so say I'm standing right here at time is equal to 0, I take out my stopwatch and I punch my stopwatch and I say, go. And so he runs a certain amount of distance, so say he goes distance is equal to 100 meters, and say he does that in 20 seconds. So time is equal to 20 seconds. 100-meter dash in 20 seconds. He's not terribly fast, but it's a decent book, Maze Runner. Anyway, so here we've got time is equal to 0. I've also got distance is equal to 0. Okay, so if I'm looking for his velocity, okay, his total velocity, I can say, all right, so I'm just looking for the total distance over the total time. And so I can come up with an equation that says, okay, velocity is going to be equal to total distance, or d divided by time. Right, delta d in this case, but divided by delta time, which just means, okay, your distance at your final distance minus d naught, right? So our initial distance in this case is 0 over t minus t naught. Now in this case, our d naught and our t naught are both 0, so 0 that goes away, and so basically I just get distance over time. Okay, so once again, this guy's velocity is going to be 100 meters over 20 seconds, and I would just get, okay, he's going 5 meters per second. Now, if I'm talking about angular speed, okay, angular speed is a little bit different, okay? Because angular speed, you're not talking about distance traveled necessarily. You are talking about distance traveled, but it's going to be sort of depending on how far outside of the radius you are, right, versus versus how fast it is spinning. Okay, so instead of d, I'm going to rewrite my velocity equation here with s. Okay, because that's what we've been using here. We've got arc length right here. So if I want to think about my runner running like this, right? So instead of d, I would have some s. Okay, so I would say v is going to be equal to s divided by t. Now what I do know about s, and this goes back to what we just learned here, s is equal to r times theta. Okay, so if I wanted to rewrite this and just substitute r times theta, okay, so I would say r times theta divided by t. Okay, so now we're automatically assuming a couple things. Okay, we're assuming this runner is running around a circular track, or whatever it is. It's going around some sort of circular thing with a fixed radius, and I know what the angle is that it's traveled, right? So if it's say it's my maze runner right here, he's running in a circle, and he goes one complete circle, and he stops, right? So well, I know one complete circle is 360 degrees, or 2 pi radians. Okay, so if I wanted to solve this problem, I could say, okay, so what is the radius of my circle? Say my circle is 100 meters. So he's going 100 meters. Okay, and once again, theta. Remember, theta can't be in degrees. Theta has to be in radians. So say he's going 100 meters, and he goes one full, or the radius is 100 meters, r. He goes one full loop before he stops. So he's going 2 pi, right? If he went half of it, he would just go pi. In this case, he's going one full, so he's going 2 pi. In this case, say he does that, and he does it in about, let's say, 50 seconds. Okay. So how fast is he going? Now I can pull out my calculator. Okay, so I can say 200 pi divided by 50. And sure enough, if that's the case, he's picked up his pace a little bit, and he's going about 12.57 meters per second. Now, I'm going to pause this here and talk about what angular velocity is. Okay, so angular velocity is how fast something is rotating. Okay, so if I look at this equation here, and I'm going to copy this equation down on my next page here. Okay, so velocity, this is just our previous equation, is going to be equal to r times theta divided by t. Now, if just for fun, actually not just for fun, there's a very real purpose why I'm doing this. I'm going to rewrite it like this. So I'm basically just going to pull the r out front, haven't broken any algebra rules or angered any of the algebra gods. So here I've got the radius is equal to, or radius times theta divided by t. Now theta divided by t is how fast something is spinning with respect to time. Okay? So you can imagine if something is spinning really slowly, right? So say it takes, say something is going 2 pi radians, or one full revolution, in 1 second, right? So it's going to be going about 6.25, or sorry, 6.28 rad per second, which is pretty quick, right? So it's every time around, every second it's going like 1, 2, 3, 4, right? So that's going to be its angular velocity. Now if I want to do that again, but instead of 2 pi over 1, if the time all of a sudden is shortened, say it does it in 0.1 seconds, okay? So I'd say 2 pi over 0.1. So it's doing it in 1/10 of a second, which is going to be going like this, right? So 10 times faster. So now it's going 62.8 rad per second. Okay. So now if I wanted to stop thinking about it in terms of radians, but in terms of revolutions, right? So say one cycle or one loop every second. So I could, instead of calling this 6.28 rad per second, I could call it, instead of 2 pi divided by 1, I'd just say this is going to be equal to, same thing, I'm going to say 1 revolution over 1 second. This is going to be 1 RPM, or RPS, revolution per second. Now if I want to do the same thing that I did here, instead of 2 pi over 0.1, if I did 1 revolution over 0.1 seconds, I come up with 10 RPS, revolutions per second, right? Now let me go ahead. So this theta divided by time. This is angular speed. So theta divided by, that's an ugly theta, theta divided by time is going to be equal to angular speed. And this can also be written as, instead of theta divided by t, this is also written as omega, which is sort of a W. I'm kind of butchering it here. But omega is going to be equal to angular speed. Okay, so just be aware. Okay, so if I take this omega, theta over t, and I start plugging things in here, I can see that v, instead of going to be equal to r times theta divided by t, I can say v is going to be equal to r times omega. So if I know the radius and I know the angular speed, then I can really quickly calculate how fast something is going. Okay, so I promised I was going to keep these videos short. I'm going to stop it here. Tomorrow we're going to jump into a bunch of examples, a bunch of problems, and tomorrow's lecture is just going to be a whole review of this entire section of the book. So everything we've learned from angles, arc length, and coterminal angles, etc., etc., etc. Okay, so I'll see you guys tomorrow in class.